Welcome to Alaska Earthquake Science Facts. I'm Carl Tate. The 3 nuclear tests on Amchitka Island were recorded by local, regional, and global seismic stations that led to scientific discoveries. Here's our setting for Amchitka Island out in the western Aleutians along the arc of volcanoes along the subduction zone. The 3 tests were Longshot in 1965, Milrow 1969, Cannakin in 1971, and some information on those is shown here. Cannakin, the last one, was the largest of these tests. The global scale, we can think about stations recording these events. This is 1971, the global worldwide network of standard seismograph stations. Here's College, close to campus here in Fairbanks. This shows the location of Amchitka, and this shows the coverage of the stations at least available to the US. We can also see that this events were studied at a continental scale. This is from a report showing the stations in Alaska, College being one of them, ADAC, that recorded this event. And we'll see why you want to look at these wave fields at different distances from the event to learn something about the source and the structure. Stations were also installed at the regional scale. So this is Amchitka Island. There were temporary stations as well as longer running stations out in the islands offshore here. And at the very local scale, this is showing the stations on Amchitka Island. As it shows here, Milrow was detonated in 1969 to calibrate the region to establish a baseline from which to predict the effects of larger field explosions. The seismic network for this test consisted of 7 land-based seismographs supplemented by 10 short-term ocean bottom systems providing sufficient capability to monitor low-level seismic activity up to at least 50 kilometers from Milrow ground zero. It says Milrow was in fact instrumented considerably more extensive explosion-related seismic effects than observed from comparable tests in Nevada. So this is from one of the papers coming out of this by Bob Engdahl, 1971. And in the paper says, in 1969, at the request of the Atomic Energy Commission, the National Ocean Survey undertook an Aleutian seismic program, which included the interpretation and reduction of data from a network of seismographs that continuously monitored activity in the Aleutian Islands in Alaska. This seismic network had 3 purposes. First, to monitor the seismicity of the entire Aleutian arc, to monitor extremely low-level seismic activity in the Amchitka Island region to describe accurately the natural patterns which would be observable on a larger scale over longer periods of time. In other words, you put out more stations and you can get a lot more events that can fill in sort of the maps that you see at the left in a shorter amount of time. You don't have to wait as long, because you can record smaller events. And finally, to document the effects from underground nuclear explosions on Amchitka Island. And this shows, very early cross-section of it's called the Benioff zone. This is the subducting Pacific plate going down to the north. This shows the trench here where the plate dives below the upper plate. And you can see these events going down to a couple hundred kilometers, reflecting the deformation and events occurring within the subducting slab. But a nice picture in the early era of plate tectonics, revealing what we now know to be plates going down and subducting. So using these events, we could look at stations far away to characterize the source. And this is one example, teleseismic, meaning far away, source parameters of the Longshot, Milrow, and Cannakin nuclear explosions. We can also characterize the structure beneath faraway stations. So using the Cannakin blast signal and seeing how it is recorded on, say, a large array of stations in Japan, this author was pointing out that the variations in when the wave arrived in Japan was attributed to changes in the type of structure below Japan. So it's very early stage of seismic imaging using the explosion as a source of energy to look at the variations in the arrival time of that P wave. And here's another one. This one is from Australian variations in Australian upper mantle structure from observations of the Canachin explosion. So again, using this explosion and the wave field coming from it to look at variations in structure on far parts of the planet. This shows Sydney here and some stations out here and looking at the time difference of the wave arriving there. Of course, all these waves emanate from the exact same time from the Canachin explosion, but the time it takes to reach these recorded stations depends on the structure they're going through, which here was interpreted to be these different parts of Australia. One of the things that was discovered from this kind of test was actually that there's challenges in locating earthquakes in subduction zones. It says subduction zone calibration and teleseismic relocation of thrust zone events in the central Aleutian Islands. This is the same lead author from the Amchitka study from a decade earlier. And it says, for these earthquakes, they're systematically mislocated by about 40 kilometers to the north relative to the local network solutions. In other words, with stations right on top of the event where we're sure we know what the locations are, when we remove that information and just use stations from far away, you get an event that's 40 kilometers to the north and actually off by depth too. And he says, we attribute the mislocation to travel time anomalies produced by the higher P wave velocity in the subducting slab. And this shows a picture of these mislocations. So this at the base of the vector, the tail is where the location should be from the local solution. But when you use the teleseismic data, everything moves north by 40 kilometers. And this matters for trying to understand the tectonics and activity of a subducting slab and the interaction with the plate interface where this megathrust or the main plate boundary is. You can see in cross section here with the downgoing plate that they're also systematically located deeper. They're to the north, but they're also deeper relative to the trend. So this would be south to north here. Finally, just to show a plot that's kind of an interesting way of looking at earthquake activity. This appeared in Willis 1972. And you can see here, this is longitude from west to east, and it's time from 1963 to 1972. So there's a lot to think about here about what you're looking at, but it's a way of looking at activity along the arc. I mean, you could say that, well, at 160 degrees, there's not very much activity at all. But some of the big things that jump out are 1965, which is a magnitude 8.7 Rat Islands event out here in the Aleutians. And this is the 1964 magnitude 9.2 with large numbers of aftershocks and activity, especially in this zone here. And this is the context for looking at the nuclear tests, the Canachin tests, Milrow, and the first one, which is Longshot. And at least at this scale, you can see that the activity from those in the big picture, these are barely visible, but it's a reminder of the connection between seismology and nuclear monitoring in both, using the same instruments to look at these events, both locally, regionally, and globally. So it's an interesting perspective on earthquake activity in this section of the Aleutians. Takeaway topics: we can locate and characterize explosions similar to how we locate and characterize earthquakes. The same tools are being used in the same recordings to look at both earthquakes and nuclear explosions. We can use the known source location and its origin time to probe variations in the subsurface earth structure, as was done in Australia and Japan for these Alaska tests. And that hints at using these events and earthquakes for imaging Earth structure. Earthquakes and nuclear tests in the Aleutian Alaska subduction zone revealed that the presence of the subducting slab must be taken into account in order to properly locate earthquakes. Earthquake location is kind of a fundamental objective of operational settings, such as, say, the Alaska Earthquake Center. Thank you for watching. Please stick around for supplemental material.